All right, I want to talk about one-to-one correspondence. And a one-to-one correspondence is simply we're going to take something from one group and something from another group and pair them together. And we start learning one-to-one correspondence when we're like 2 years old, when you first start learning to count. Your mom or grandmother or someone might have counted out like goldfish or M&Ms, and they would say 1, and they would put a goldfish or a cookie or a crack in your hand. And then you would say 2, and you would put another one, and then you would say 3. So you were learning that there was a number that went with the item, and you would pair each item with a number. So we're going to take this idea and apply it to sets of things that might be abstract, so not goldfish or M&Ms. So I have a set of numbers, the set 1, 2, 3, 4, and then a set of symbols. If there is a one-to-one correspondence, I should be able to take every number in this set and pair it with a symbol in this set with no overlapping. If you see, if I send 1 to the heart, 2 to the asterisk, and then 3 to the circle, there's not a pair to go with 4. So this cannot be written in a one-to-one correspondence. Another, probably simpler way to think about it is this first set has 4 elements in it. 1, 2, 3, 4, 4 different things. This second set only has 3 elements in it, so I can't make a one-to-one correspondence. If I change this to the set just 1, 2, 3, and then my set of symbols, now there is a one-to-one correspondence. There are 3 elements in this set and 3 elements in my symbol set. So I can send 1 to the heart, 2 to the star, and 3 to the circle. So there's 1 number for 1 symbol. So there is a one-to-one correspondence. Now let's talk about sets that are infinite. So infinite sets might be like our natural numbers that we learned about earlier in the semester. So the natural numbers start with 1 and go to infinity. So things with our ellipse down here tell us that they're infinite. Well, I'm going to take these natural numbers and make a correspondence, a one-to-one correspondence with, let's say, the multiples of 3. So the multiples of 3 start with 3, 3 times 1, 3 times 2, 3 times 3, 3 times 4, etc. Now I can make a one-to-one correspondence with these because they're both infinitely long. There's infinitely many natural numbers. I can go on to forever. I can keep counting and never stop. And there are infinitely many multiples of 3. So the multiples of 3, there's 3 times a million, 3 times a billion. They keep going on forever. They never, never, never stop. So what I do is I set up this little pattern. I'm going to have my natural numbers, and I'm going to make sure the little dot there tells me they're just going forever. I'm going to compare it to this other set. And anytime we're talking about these infinite sets, we're going to be comparing our natural numbers. So it's going to have the natural numbers and then another set that's infinite. So I'm saying I'm going to send the number 1 to the number 3 and call that a pair. The number 2 is going to be paired with the number 6, the number 3 with the number 12, and 4's pair is going to be, the number 3 with the number 9, and 4's pair is going to be with the number 12. Now I do have to do one more little piece of work on this. I need to write a little algebraic equation. So my algebraic equation for natural numbers, I'm going to use the letter N for natural numbers. I'm going to say, how can I take this number N and turn it in to the numbers over here in my multiples of 3? So how do I turn 1 into 3? Using arithmetic. How do I turn 2 into 6 and 3 into 9? And it looks like each time we're multiplying by 3. If I take 1 and multiply it by 3, I get out 3. If I take 2 and multiply it by 3, I get out 6. If I take 3 and multiply it by 3, I get out 9. So this tells me I could find the natural number and the multiple of 3, they get paired together no matter where they might be. For instance, if I had the number 30 in my natural numbers, its pair would be 90. 30 times 3. That's what this little formula tells me. Let me do another example comparing the natural numbers to this other set. This one's going to be a little bit more complicated. So I'm going to compare it to the set that starts with 15. And it's going to count by 2. So 15, 17, 19, 21, etc. I'm going to do the same thing that I did in my last example. I'm going to take my natural numbers and find their partner or their pair. The first natural number is 1. The first number in this set is 15. The second natural number is 2. The second number in this other set is 17, etc. The third number is going to be 19, and the fourth number is going to be 21. So these are my pairings. Now I need to figure out this algebraic equation down at the bottom. I'm always going to use n for my natural numbers. My natural numbers are going to go to n. And I need to figure out the little equation that's going to get out these numbers. If I were to plug in n to my equation, I should get out 15. And there's a trick to doing this. 2 steps. The first step is to see what you're counting by. And I kind of already hinted to that at the beginning. I said we were going to start at 15 and count by 2s. So each one of these, I counted by 2s. That's going to be the number that goes in front of n. So I'm going to start with 2n because I was counting by 2s. Well, I know that's not our final answer. If I plugged in 1 and multiplied by 2, I don't get out 15. 2 times 2 doesn't give me 17. 3 times 2 doesn't give me 19. So I'm missing a piece. I'm going to be missing this piece right here. So I have, if I plug in 1, I get out 2 times 1, which is 2. But I needed that to be 15. So it looks like I'm at 2 and I need to get to 15. I need to add 13. Again, I was at 2 with my 2n and I needed to get to 15. So the difference between 2 and 15 is 13. I'm going to check it now. If I have 2 times 2 plus 13. 2 times 2 is 4, plus 13 gives me my answer of 17. I know this is a little tricky, so I'm going to do one more where we have both of these steps. I'm always going to be comparing to my natural numbers. I'm going to get a new set here. Let's say we start with 10. And count by 3s this time. So 10, 13, 16, 19, etc. Both of these infinite sets, they're infinite because of the ellipses at the end, will be given to us. We have to set up the one-to-one correspondence. So I'm going to have my natural numbers. I'm going to pair them with my set that I was given, this one that starts at 10. And I have to come up with a formula at the end. I know it's going to be n for natural numbers. The first thing I do is say, all right, what am I counting by? I already talked about it. I said we're going to count by 3s. This number is going to be what goes in front of n, so 3n. And I know I'm missing a piece right here. So I got to figure out that missing piece. So I'm going to figure out where I'm at. If I plug in 1, I've got 3 times 1. That gets me out 3. But I need my answer to be 7. I'm at 3 and I need it to be 7. That means I'm at 3, I need it to be 10. So that means I'm going to add 7. So my formula is going to be 3n plus 7. Let me check that real fast. By doing 2, I plug in 2. 3 times 2 gives me 3 times 2 plus 7. It's going to give me 6 plus 7, or 13, which is exactly what I need it to be. If you're having trouble, watch the video again, and then go give the homework a try, and feel free to stop by my office if you have any other questions.